Welcome to Module 13. This module will focus on SQL injection. Many web applications today make use of databases to store data. If that's the case, SQL queries need to be an integral part of these applications. SQL queries are used to retrieve and pre-process specific data stored in a site database. These queries are often generated dynamically using input parameters passed through the GET and POST methods. An SQL injection vulnerability occurs when users can manipulate the final content of an executed SQL query. Take a look at a sample script designed to illustrate this. The first page we'll discuss is a simple login form which first connects to a database. A form is displayed. If the form is passed to a script, an SQL query is generated which retrieves appropriate database records for the submitted user credentials. If this operation is successful, an appropriate message will be displayed. If it fails, a corresponding message will appear to the user. Let's see how the script works. Here's the login script. We have successfully logged in because the database contains records for the admin user holding the test password. Now enter invalid user credentials. As expected, the login has failed. Notice that user-supplied data is not filtered or validated in any manner. This means that users have control over the result SQL query. Try to think what a potential attacker could do in this situation. Let's see what will happen if the following data is sent. While these credentials are certainly invalid, altering the SQL query results in a successful login. Take a look at another example. We can see here a simple application which loads articles using an identifier passed through GET. The ID1 value holds a sample article with the content, test article. Let's see what will happen if we change the query slightly. Since no content has been displayed, we might assume that the application is vulnerable to SQL injection attacks. Let's try to verify if this is the case. Add in a string which will constitute an invalid identifier, but which won't change the behavior of an SQL query in which it's placed. As we can see, the approach has worked. This confirms our suspicion. We may freely alter the end of an SQL query. Still, we need to find out which table the query works and how many columns the table has. By using the order by keyword used to sort records, you may discover the number of columns returned by an SQL query. Order by might be used to specify the number of a column by which columns will be ordered. If the number is greater than the amount of columns returned by the query will be incorrect and won't return the requested result. If we submit 1 as the specified value, the columns will be sorted by the first column, which should always exist. Confirm this by entering the following address. Let's now try to specify as the value a number so great it probably won't correspond to the number of columns returned by a query. In this way, we'll make sure the query is working as predicted. As we can see, the query indeed has not contained 100 columns. This is why no content has been displayed. The database engine has interpreted the query as incorrect. Now, let's submit several values to discover the exact number of columns. As we can see, the query fails with the parameter of 10. It does not work with 5. The operation is successful with the number 2, so we know that there are at least 2 columns, but no more than 5. Let's try with 3. The query fails for this value, which means that it returns exactly 2 columns. We'll use the union function, which allows you to combine result sets of select statements from both sides. Union requires the statements to have the same number of columns. The attempt has succeeded. We now know that the database supports the union function. None of the values we passed has been displayed. The reason for this is that the page only displays the first result set, while the ignored second result is the one which was added by union. Once we add the AND 1 equals 0 string to the first request, we'll cause it to return no results, and so our request which is glued by union becomes the only request. This time, one of the numbers we passed in a select statement has been displayed. The displayed number 2 means that the value of the second column is displayed on the page and may be used for passing data we'd like to retrieve from the database. Let's use several standard functions. The user function returns the name of the current database user. In this case, this is the test user working on a computer where a database server has been launched. The version function returns the version of the database. What else could be done in this situation? Starting with MySQL 5, the software is equipped with information schema, a special database used for storing information on the structure of all other databases and tables, which can be accessed by users. This is a form of a database reflection mechanism. The first way of using it in SQL injection attacks entails the discovery of table names. Select Table Name from Information Schema in Tables, which contains information on all tables viewable by the current user. The head of the table contains the system tables as well as information schema tables. To discover other tables, use the limit function, which allows you to set a result range. "100 is too big," while 20 still shows the system tables. The 30 value has returned the user's table. The name looks promising. We'll now use the columns table from the information schema. As you can imagine, the file contains column names viewable by a current user. Add a condition which specifies that we're interested in user table columns. Column name is the name of a database field which contains column names. As we can see, ID is the first column name. The second is disabled attempts. The next is login, which looks interesting. The fourth column is pass. In this way, we have specified a current user and can access the user's table, which contains the login and pass fields. Using this information, we'll be able to display the contents of the table. As you can see, the first record of the table defines administrator. We can also display the pass column to see the password unencrypted. To prevent this, we need to remember several steps. The first step is to put all parameters in quotes. While this isn't a security measure per se, it is the basis allowing for the data to be filtered further. In the case of this script, the identifier is always a numerical value. Using the intval function, we can make sure that the return value will always be a number. If a string is placed at the start of a function, the 0 value will be returned. Let's see how this works in practice. As we can see, the attack has failed. What can be done if the query has to be made up of strings? Notice that if attackers are to manipulate the content of an SQL query, they need to use quotes. You can now filter input data for quotes using the MySQL Real Escape, preg replace, add slashes, or HTML special cars functions. The HTML special cars function can also help you protect yourself from XSS attacks. Let's see if this works. As you can see, this time the attack has failed as well. Let's also see what could happen if a user working with a database has rights to operate on files. The rights are set while creating users or granted by administrator. A normal user very rarely has file operation rights, but they are enabled by default for the root user. Use the load file function in SQL, which enables you to load the contents of the file. As you can see, the contents of PHP-ini have been displayed. The function enables users to access all files to which the current database server user has access rights. Logging data to a file is also possible. First, let's prepare a string which will be saved in the website directory. A PHP code which calls the php-info function. The directory contains only 2 files. As you can see, a test PHP file has been created after sending a request. You can even run it. The value 1 comes from our select statement, as the select into out file function logs all columns returned by a query. This won't do much to stop an attacker from saving the file with PHP code. So how do we protect ourselves against SQL injection attacks? As you can see, if database user configuration is poor, file operation becomes possible. Remember, you shouldn't work with your database using the root account, as the root user has full file rights, permissions to operate on files, and unlimited access to all database tables. It's good to disable file operation permissions while creating new database users. That's all in Module 13. Thanks for your attention, and see you in the next module, which will focus on cross-site scripting vulnerabilities.